Cool, we live? Brilliant. Hi everyone, I'm Max Clark. I'm here today with Andrii Kolesnyk for the latest edition of the Pizza Sessions series. Thank you for joining us. Today we're going to be talking about, or Andrii is going to be talking about data privacy, in particular differential privacy. And so we're looking forward to, I guess, digging into something a little different to usual. As always, we're going to kick off our session with a quick sort of chat, Q&A, I hesitate to say interview, with Andrii, who's a data engineer here at our team at PA Consulting. And then we'll go into the real meat of the session with the slides and dig into some of the details around differential privacy. Before we go into our chat, I'm going to do a little bit of housekeeping about the Pizza Sessions series. So what are the Pizza Sessions? They're a deeply technical data science forum focused on detailed discussion of topics, techniques, and ideas in the space. Why do we do these? We do them because data science has always been founded on active, engaged communities. That's where all the innovation comes from. It's the best way to learn from others around you and share, again, the things that make it all tick. We run these sessions every 4 to 6 weeks, and all the previous sessions are recorded and up on our YouTube, so feel free to check them out. And the only other thing to note is if you're interested in seeing what's around the corner, we do have a meetup network where you can keep up with all the forthcoming events. And if there's anything in particular you'd like us to run a session on, feel free to reach out and post on there and we can set that up. So with that housekeeping out the way, let's get into it. Lovely to see you, Andrii. Nice to be here today.
Yep.
And as always, we will lead off with, I guess, a chance for you to introduce yourself.
Mm-hmm. Certainly, yeah. Hello everyone, my name is Andrii Kolesnyk. As Max has sweetly said, I'm a data engineer with PA Consulting for the last 3 months, so a recent joiner. Previously, I've worked for the NHS, so in healthcare for the last 5 years prior to joining here. And before that, my whole background comes from biomedicine, primarily like neuroscience, neuroimaging, and yeah, so most of the education and work within healthcare sector, and data engineering being the main work because I kind of fell into it and just went with the flow. Yep.
That makes sense. With a background that's quite specific in that biomedicine healthcare space, what led you to make that move to a technical consultancy like PA?
Yeah. Well, actually, I've tried to join PA around 5 years ago as well, so I felt, yeah, so it's like, tried, failed, so I was like looking somewhere else to join again 5 years later, and remembering what good things I've heard about PA, I thought, I noticed there was actually a job opening for data engineers, and so I thought, oh, actually, this falls right down my alley, so I thought, let me try and apply again, and because I did remember some good work they did with NHS and other kind of public services and governments, so I was like, okay, this sounds interesting, let me try again. And I reapplied, basically, yeah. That's the short story of it, yeah.
Oh, working out well. So, on to the question that is on my mind. Today's Pizza Session topic is data privacy. Big topic, obviously, but it really jumped out at me because of the usual sort of content for this series. Often in these seminars, we're talking about techniques or maybe an approach, and the focus is often improving the quality in some way of like a model's output, for example. So, or adding an extra item to your tool belt to tackle something in a different way. But it is often with a mind to sort of that quantifiable output. Data privacy and data privacy awareness obviously is extremely useful, and we're going to dig into that. But it's quite a different type of useful, at least on the surface. So what brought you to wanting to talk about data privacy today in this forum?
Yeah, well, excellent actually, because the first thing it did, because it came as a hot topic or as a big topic, especially within the healthcare field itself, particularly because we had a lot of clinical trials running around, and it became more noticeable that how do you make patients consent to clinical trials or participate in trials overall, but also kind of be happy to make sure that they are happy to share their data. So that was one of the concerns. And another topic in general that, yeah, it's like wherever we go nowadays, there's so much data flowing around, but as much as we're trying to add GDPR and all of these kind of policies and methods to regulate it, when it comes to technical discussions, as you've said, most of the time, for example, whether it is building data pipelines or models, we concentrate a lot more on technical aspects of it, but we never bring these kind of policy or human factors into them as well. So that's where my interest in data privacy came about to be. And yeah, so since then, that's why I was kind of looking more and more into it, and here we are now. Yeah.
Fantastic. I'll follow up with a slightly cheeky question, because
please,
your background is in data engineering. I know we're going to have a lot of data scientists in the room and watching on the video today. The cheeky question is, why does data privacy matter to a data scientist?
That's a good question. Well, I believe it's in their interest to kind of defend the data, the individuality of every person and every person's right to their data ownership, and it is useful, yeah, for any data scientist to be aware. It's like how the data is used by. It's like where did this data go? Because in the end of the day, they might be also one of those consumers of the data, but also their data might be used somewhere else, and so they have to be aware. It's like of the consents and also of people's freedom and the right to their own data. And again, it's becoming like as a big topic now in discussions, like how people's data is used, and it's their right to be aware how their data is used and whether it should be used or not in multiple applications, especially whether it's for right things or not. So the main topic being that it's always the data has to be used only for the right purposes or where they're intended to be, not for everything altogether, whenever, however. Yeah, that's kind of my gist of things. Or like as a guy who doesn't do data science much, but like sees a lot of it.
That makes sense. I think that makes a lot of sense. It's easy to think in the moment that, oh, I mean, somebody else has to worry about this down the line, but I mean, what you're doing quite quickly becomes down the line. Hopefully, if you're doing it well, at least.
Yeah, pretty much. Yeah.
Thank you, Andrii, for fielding a few tricky questions. I hope that's I think that'll set the scene nicely for the rest of the discussion. At this point, I will hand over to you to start kicking through the bulk of the presentation.
All right, cool. Thank you, Max.
If anybody in the room has any questions during Andrei's presentation, just shout out, and I will try and drag you in. We'll take them as we go. Over to you.
Cool. Hello, everyone, again. Yep. So today we're going to be talking about data privacy, and particularly because in the past the pursuit of privacy was an absolute or nothing game, all or nothing game. The best way to protect our data was always hiding it behind the rock solid firewalls, right? Guarded with like multiple n-factor authentications. But nowadays, the strategy is motivated. So the strategy used to be motivated by the reality that data is locked away in kind of mathematical safe, that it can be used for scientific research, it couldn't be aggregated for any statistical analysis, or analyzed to train machine learning algorithms. And one potential answer would have been differential privacy, because it would open up the possibility for all of these tasks and more. It will make simpler and safer data sharing before we reach maybe some efficient homomorphic encryptions, but that's like a long haul. So today, we're setting this scene about differential privacy and keeping like access to information practical but also private. I will try to talk about the general consensus, what data privacy is. Then we'll jump on to some linkage attacks as well as leakage, so distributed training and leakage attacks. Differential privacy itself as a definition, some of its properties, and then we'll finish up with some machine learning with DP. Yeah. So, without further ado, data privacy. What is it? So, I thought the first step should be taken as clarification what privacy is and what it isn't, and so specifically privacy versus security, because this topic can kind of become very synonymous when it comes to Googling things around or talking about things. And so security concerns itself with unauthorized access, whereas privacy concerns itself more with proper handling, processing, storaging, and usage of personal information. One of the kind of good sentences about it is you can have privacy without security, but you can have security without privacy. A very simplified example for this is, let's say you have a house, there's a hole in the wall, right? No windows. Everyone can see your furniture, what's inside. You have neither privacy nor security. Then you get a window for it, right? So now you feel a little more secure, unless somebody smashes the window, but you have a window, right? But somebody still can see what's inside, right? They can peek through. If you add some curtains to it, then suddenly you have privacy and security sorted out for yourself, right? So that's kind of the oversimplified but good example of kind of differentiator between the two. Now, of course, once we've settled with definitions, we'll jump straight to the threats to data privacy. And one of the key threats to data privacy is de-anonymization. So this long-winded word basically means that if you have any kind of data which could be anonymized by any means, such, for example, nowadays it's obscuring it, using k-anonymity, for example, like creating groups for different variables or categories. There are two potential ways you could use to kind of get some of that information back. One of them is linkage attacks. So these are utilizing auxiliary databases or information to kind of connect the dots, so to say, and get some of the information. The other is called leakage attacks. So this uses information leaked from training models, whether it's class label parameters or as well as gradients that are used for optimizing the training model and kind of reverse engineering it, basically. The latter is really important nowadays because in the face of cloud computing and distributed training models that we'll touch upon later. Yeah. So, linkage attacks, right? What are they about? So, linkage attacks, again, have two great examples. One of them was from the year 1997, called Find the Governor. And so what has happened was, in the US in 1997, the insurance company has released medical records, and the dear governor of Cambridge, Massachusetts at that time, William Weld, was very proud that the data is completely anonymized, all the identifiers were removed, everyone is happy. But, there's always a but, there was one researcher, Latanya Sweeney, who was a graduate at university at that time, and she took it as a challenge. So what she did, she went to voters' commission boardroom. She paid $20 to get all the voters' information in the Cambridge city. And because William's postcode and details were public, she could easily manage to find all the other identifiable data about him, because there were only 6 people with the same age. There were only 3 of them who were men, and only 1 was living in the same postcode. So using that information, she could easily find William's specific medical records, and as a joke, she sent it to his office, basically stating, here we are, I know what you've done, or what you've been through. The good thing is that all of this, although this was relatively a light research, it did give a lot of groundwork to what became later on in 2003 the HIPAA privacy rule in the US. And it kind of gave a bigger discussion to a lot of topics around data privacy. The second example is a bit more modern, so to say. So 10 years later, Netflix, as they were climbing through their business and developing their own machine learning models because they wanted to have better understanding of their customers and whatnot, they anonymized their data, given all the learning experience they've had from the governor story and everything. So they anonymized a lot more information, but they still left out some of the things available. And one of these things were movie ratings as well as timestamps, right? And at first, it was clear that the data is pretty much anonymized, but again, in University of Texas, there were 2 researchers, Arvind Narayanan and Vitaly Shmatikov, who essentially took it as a challenge to try and find out if they can actually connect any of that available data to somewhere else. And what they found is IMDb database. And so using the movie rankings from IMDb and the timestamps, along with publicly available usernames, because some of the users are very open-minded, so they use their last name, first name, or like something very similar, they could actually identify some, yeah, so they could back identify some of the users from the movie ratings in the Netflix database, and so on and so on. So again, they basically said, if there is a will and a way, you could actually find more information than you often think is not there, right? So these are the examples of linkage attacks. Now we'll go to the fun leakage attacks. So leakage attacks, as I've mentioned previously, they utilize more of parameters from data models or trained models. But before we jump into them specifically, I wanted to touch a bit more on the distributed training. So distributed training, or as often known nowadays as well as federated learning, consists primarily of two potential workflows. One is either with centralized server and one is with peer-to-peer. In the centralized server, as denoted by the blue squares, the training nodes could be either different institutions, they could be different buildings, offices, 3 different PCs, doesn't matter. As long as it's just 3 separate units of and more, they create their own kind of, they train their model with their local data, in this case scenario, private data. And then once they've done training that data or that model, they take the parameters out of that model and they feed it into a centralized server, whereby all of these parameters are summarized together and used to train, again, the main central model, so to say. And then that process is recycled until they're happy, basically, with the accuracy and performance of the model. The second variety of it is distributed training with peer-to-peer, whereby there is no centralized server, but all the nodes that are training their model together, they can cross-share them, as you can see in the third little cube. So they can exchange these parameters on the go, and then they improve the overall model for everyone across all the 4 nodes, right? So that's kind of the overview of the workflow. The importance of this is that these examples were first as research papers. They were all existing for the past 10 years, whether in hospital studies, some also geological studies. But then all of that research has also transformed into some kind of big commercial projects, or like, for example, now, earlier in the year, NHS England wanted to have a big plans of investing in like $250 million money into building a federated data platform. So that's why it will be an important consideration or an assumption to take on when you deal with such big investment, and also dealing with not only technical bits and aspects, but also these regulatory aspects of like data privacy and stuff. So once we've set the scene with distributed training, we jump back to our kind of 2 types of leakage attacks. So one of them is called conventional shallow leakage, CSL, and the other one is deep leakage from gradients, DLG. Again, these terms are taken all from research papers, so hopefully like the acronyms will become better. But this is what we are given now. So the earlier one, CSL, it usually utilizes some property inferences or like class labels from the training models and adds it to generative adversarial networks and creates some of like representation of what training data could be. But deep leakage from gradients goes directly by taking the gradients from the training models and runs some optimization processes or like algorithms to essentially try to map that particular gradient of like from the training model to whatever the adversary might have. So adversary will start with some label data and some gradient, and they'll try to map it basically, if that makes sense. Where it may occur, as coming back to our old graph, the little kaboom icons, as I call them, indicate where the attack might happen. So for example, with centralized server, it might be either at the point where all the locals are sending the main model to the server, or at the point when the summation of the parameters is done and you're sending that information back to back again to distribute the global model. When it happens with peer-to-peer, essentially whenever they're exchanging all of their data. So technically, actually, you don't actually need to interrupt. With central server, you might just need to interrupt any connection to the central server, but with peer-to-peers, you just need one peer to get the rest of information because somebody will end up sending information to each other, right? Now to some kind of practical views. So this was from a paper from 2019 from guys in MIT who were showcasing their algorithm for DLG and how they were trying to get the data. And they were comparing it to somebody called Luca Mellis from UCL and Cornell who were using GAN or CSL to actually generate the images. And as you can see, I'll go from the right to left. So on the right-hand side, we have the ground truth. But then Mellis, using some class labels that they got from the model, could regenerate some synthetic-looking data. And as you can see, the simpler the data, like MNIST, right? Then it has very kind of similar design or the image. But as it goes down to more detailed stuff, then you can see like there's not much clarity. You can guess it's maybe a person, but nothing more. With DLG, as much as they go, because they start with complete noise, and as they're improving their own gradient in accordance to the gradient they got from the training model, they're getting closer and closer and closer with some iterations over to look exactly like the actual image used for the training model, right? So it's just a refinement process.
Yeah.
Yes?
Do they have to keep querying the model when they're to optimize the things so that they have the model and they can keep?
Yeah. So they keep getting and attacking it, as much as they want, So that's the main premise behind it, is that with gradients, why the people felt safe about it, so therefore they said we can put our model on the public domain, we can put our gradients on public domain, because as long as they just have the model and gradients, life is good. So we don't actually need to share any training data. So that was the safety point for them. But and so in mathematical terms, or like this is the kind of process flow that the malicious attacker would have to follow in comparison to the normal training participant, right? And as they said here, denoted by the G, all they had to do is trying to find the loss, the perfect loss between the weights that they would get from the normal training and the weights that the malicious attacker would have to kind of improve or optimize the gradient. Of course, the world isn't perfect, so these guys still had the limitation because they used a particular optimization solver, and it had some of its own requirements, right? So for some reason, it could only work on smoothness of the network. It had some effect of it, and it also had memory limitation because the optimizer they used was called limited memory BFGS. If that makes sense to data scientists, because yes. Okay, so the interesting part of this as well, aside from this, was that the three assumptions of how to defend against deep leakage attacks were primarily gradient perturbation, gradient compression, and just reducing the precision of the inputs or like the gradients that come out after. And the one and only we'll try to concentrate on today, which is related to differential privacy, is called gradient perturbation, right? Because essentially what they're trying to do is they're trying to add noise to whether the gradient that was produced or anywhere else.
Yep.
Whew. So differential privacy. Sorry, am I running through? No. Okay. Cool. So differential privacy, right? We'll go now through the mathematical definition of it, also like just a general definition idea, what it is, some of its properties, right? So as you can see here on the graph or on this flow diagram, all the differential privacy is an analysis. So what it promises to you is that the output of differential private analysis will be roughly the same whether or not your data is contributed to it. So we can see the database D1 goes through analysis, gets some answer A, and database D2 might have my data, right? And it will get the answer B, which might be approximately similar to answer A. So that's what it kind of acts as a promise or a guarantee overall, right? So so basically, that implies that whoever sees the output won't be able to tell whether or not my data was used or what did it contain, right? So that's the hope. As a mathematical definition, it has an upper boundary, right? It is an exponential purely because out of logarithmic beauty, but also because they said it helps to deal with some divergences. But essentially, it could be just a normal 1 plus e and then like the epsilon that you can see here in the asterisk. But that epsilon is essentially a parameter that's called either the privacy parameter or budget or privacy loss. It is essentially a tuner or a knob that you can use to kind of regulate how much amount of privacy your definition provides, right? And so the smaller the value is, the more kind of privacy you input to it. So it's like if you have an epsilon of 0, basically it's extremely private, but also extremely useless because the amount of noise or any differentiation you add to it is absolutely nuts. And then the large values of epsilon require less similarity between your outputs and therefore provide less privacy. So that's why it this differential privacy acts more as a guarantee rather than an absolute term of use, like that you should apply to anywhere. So that's where we come to defining what it is not. So again, differential privacy as an indicator to what extent you will not be affected adversely by sharing your data to be used in any study or analysis, no matter what other studies, datasets, or information sources are available. But it is not a data anonymization technique, such for example k-anonymity, and it does not guarantee that what one believes to be one secret will remain secret, because as we touched upon, data security is also another aspect to consider, and therefore you can never say I'm 100% safe. So people have to be kind of aware of that. Yeah. Why differential privacy is valuable though is because of the three main reasons. One being compliance, collaboration, and reputation. Compliance is because with the recent new regulations such as GDPR, they've already done some approximate calculations and they've shown that at least since 2018, some of the European countries in summation have paid 273 million worth of fines purely for their GDPR compliance. In terms of collaboration, the differential privacy does enable you to kind of work collaboratively, as we've seen with like distributed training or distributed provision of data. Even if you do add some noise for some of the things, like for example simply sharing aggregates, it still can be useful. And also for reputation's sake, because in comparison to Europe, in US, IBM states as of their 2020 report that business loss due to factors such as diminished reputation was the largest cost factor of data breach, with a yearly average of 1.52 million. So it kind of gives numbers to the aspect of why privacy is important as well, or to be considered with developments.
Andrei, whilst we're looking at this stage, a question popped into my head. With differential privacy, you've quoted a lot of papers. Sounds like ongoing study, I might be wrong. I was just interested, how long has this been an active area of research? Is it very modern? Is it quite a long time? So it was initially written by a lady called Cynthia from US in 2006. So she has a book called Analytical Algorithms or Algorithmic Definition of Differential Privacy. So a really cool book, really thick as well. So that's why I didn't have time to go through it, but or like touch upon it more. But essentially, yeah. So it started in kind of early 2000s. So the mathematical premises for it existed before, but she kind of took it upon herself to develop more on it. Yeah. So it was done in 2006 onwards. Yeah. Cool. Any other questions? Well, no. Continue. Okay, cool. So differential privacy properties. Okay. This will be 3 essentially at the moment. So one of the primary ones is composition, which essentially allows you to deal with differential privacy. And the other one is post-processing. So composition, why is it good? Is essentially that it's the quantification of loss permits the analysis and control of cumulative privacy loss over multiple computations. So kind of understanding the behavior of differential private mechanisms under composition, and that enables you to design more complex differential private algorithms from kind of simpler building blocks. And the composition is usually either sequential or parallel, and I'll touch upon those two in the next slides. And post-processing essentially means that DP is immune to post-processing. So a data analyst without additional knowledge about the private database cannot compute a function of the output of differential private algorithm and make it kind of less differentially private.
So yeah, so once you add noise to it, that's good. But there is kind of a case to say that if you query the data with the same differential private mechanism multiple times over, you kind of reduce the privacy because you still get more answers to it, and by law of kind of large numbers or whatever it is, you average out essentially to the main bit. So yeah, so sequential composition, as it says, right? It satisfies. So privacy degrades with repeated queries, and epsilon adds up. So for example, if Bob makes the same private query with epsilon 1 twice and receives 2 different estimates, it is as if he has made a single query with a loss of epsilon 2. This is because he can average the answers together to get more accurate, less privacy preserving estimates. And so therefore, this what basically the sequential composition means. Systems can address this with a privacy budget, an absolute kind of limit of the privacy loss that any individual or group is allowed to accrue. And so therefore, private data curators have to be diligent about tackling it, who queries them and what do they ask for, right? Cool. The parallel one, or composition, refers more or less to group privacy. So even if we have a data set, we can separate it into different subsets and make it disjointed. So as long as there is like one only particular piece of information within each of the different subsets, and you apply privacy together, it's almost kind of as it adds up to one. So for example, wherever you would have your total data set to be, you apply differential privacy, and it will be like one. It will be the same if you just split it all across and apply to them separately, right? I think. Okay. So post-processing, again, as we mentioned before, it just means that it's always safe to perform arbitrary computations on the output of differential private mechanism. There is no danger of reversing the privacy protection the mechanism has provided in particular. It is fine to perform post-processing that might reduce the noise or improve the signal and mechanism output. So this is what kind of how they're dealing with if they add too much noise to some of their data. And then in fact, many sophisticated differentially private algorithms make sure use of post-processing to reduce the noise and improve the accuracy of their results. Yeah. And so the other implication of post-processing property is that differential privacy provides resistance against privacy attacks based on auxiliary information. For example, the function G might contain some auxiliary information about elements of the dataset and attempt to perform a linkage attack using this information. But the post-processing property says that such an attack is limited in its effectiveness by the privacy parameter, right, by the epsilon. And so therefore, regardless of any auxiliary information contained in G, it will be useless, so to say. Yeah. So there's no direct kind of link. Yeah. That's kind of it for definitions and properties and all of those things. And now to the main meat of examples later on, machine learning with DP, right? So at present, there are two popular kind of methods with it. So one related to working directly with gradients and adding noise to the gradients, specifically stochastic gradient descents, right? Because they're the most popular. And the other one is called PATE, but I'll just leave a link to that. Yeah, because it's a pizza session on its own. Yeah. So with stochastic gradient descent, just a reminder. So we have some sensitive training data. As the model kind of tries to optimize itself, the gradient will go over the batches of, or mini batches of the training data, right? And then it will create the set of gradients that will then be averaged with their weights plugged back into the actual model, and repeat that model like over a number of iterations until you're happy with the accuracy, right? You can underfit, overfit, but essentially, yeah. With the differential privacy, we're adding two steps to it. So one of them is called clipping the gradients, right? So it either can be clipping the gradient directly or clipping just the examples per example, because then you're not working with sensitivities of the gradient itself. So it's like, so you don't have to kind of expect how far it will explode or not. So that's why they said actually if you work with the examples, it will be easier to kind of not predict, but be aware of how far the dimensions might go crazy or not. And then once those are averaged, so once the clipped gradients are averaged, you add some noise to it, and then you feed it back to the model, and you work over it like that. Yeah. So that's kind of the gist of how stochastic gradient descent works and operates with differential privacy. And the most famous mechanisms for adding the noise were either Gaussian or Laplacian. Laplace? Yeah, that's kind of it. Now I'll happily go to the examples. Yes. Oof, damn. Oh yeah, sorry, I have to go to examples. Yes, I forgot. It's like I forgot how the screens work. Sorry, guys. Okay, so so we have two examples today. One of them will be working directly from kind of rebuilding a model and then trying to train it on some features and labels. There is no kind of business tactic to it. It's purely just to show the theory behind how it operates and works, right?
You might want to zoom in.
Sorry? Zoom in?
You might want to zoom in.
Okay. Does anyone see? Oh, this, yeah, okay, cool. So, before we kind of initiate with the rest of the things, I did define some Gaussian and Laplace equations. Well, not I did. So this material is available as well in the link I'll provide. So it goes a lot more deeper on discussion of differential privacy in different chapters. It's a wonderfully written kind of piece of work, right? So these are my kind of feature vectors and the labels, right? I'll rerun them all together. Yeah. This create the training sets. This just to showcase that we load. So at first we'll load the logistic regression model, right, and to show how it predicts. But then we try to rebuild our own, because then we can work out different things and aspects of it, right? And so this is the prediction at the moment. We just define a function for it, which we'll later on use with our own models and work through. Sorry, I'll just click through just to make sure it all operates. This will be the gradient descent that we get. And then after that, as we refer to the average, as we refer to the image before, we have to average the gradients themselves, right? And this is the result we get as the output. And then we have to iterate it over all the mini batches of the data, right? Mm-hmm. So that's why we have the iteration thing added to it as well. And as the cherry topping, we have to also calculate the accuracy of it, right? So at the moment, the model, so to say, gets like 77%, right? After initial 10 iterations. So as the description goes here, like, yeah, after 10 iterations, it's only 78. It's not as bad. It's not comparing to scikit-learn, but yeah. And then we'll go into the gradient descent with differential privacy. So before we do that, we have to define some functions around actually clipping the same information. So as we have seen here on the second slide. Sorry, does the slide show? Yeah. So yeah, so as we saw here, like per example gradient, we do have to clip them first, and then we average them out. And based on the average gradient, then we add the noise as well to it. So this is the function that will do the clipping, right? And then this is the function that will summarize the gradients for us. And then we will put it all together into one nice function called noisy gradient descent, whereby we add some Laplace to the noisy counts, but then we also add the Gaussian thing to our gradients that we try to summarize here after all of their clipping. And all of that will have to kind of give us some better gradient that we can plug in back to the model, if that makes sense overall, right? Okay, and so after working with that, we can kind of get the accuracy overall. And in this case scenario, the delta is only used for sensitivity of these different Gaussian and Laplace methods. And then the 0.1 is our kind of theoretical epsilon. So in this case scenario, it's like, it's not 10% because you could also make it from 0.1 to 2, 3, so it could be any number. But in other theory, we can see that if I run this, it will take a few minutes to run. But we can see that indicates that as the epsilon gets smaller and smaller, the accuracy of the model that you produce will reduce, because essentially what you're trying to say is that with 0 epsilon, you're ensuring the most private data, but it also is the most useless training model because you have 50% accuracy only. And so that's where it comes the importance of leveraging this epsilon knob to define how private should be your data or not. So that's kind of the simple logistic regression example that I found. Of course, you could also use this not only in the training machine models and stuff, but you can also apply it to querying data. So that's what's been used popularly by Uber and other big companies when they're gathering their information. So before they're even trying to use it anywhere else, they can use differential privacy, basically adding some noise to their main kind of queries, such as summations, averages, and counts, to produce some approximate numbers, but not actual things, because then it kind of gives the customer also awareness that customer's exact data is not used. It's the best approximation. So that's kind of default security almost. So yeah, so that's the example from here. Now we'll go back to our example of the GLG. So as we remember here, so this is the example that we saw before, and the researchers have been kind enough to produce the code for it, so we can actually try and utilize it. So before I jump into it, zoom. Yeah, I'm trying to. It doesn't zoom. Wait, what? How does it zoom? What? How do you?
Could it be Control Plus?
Oh, sorry, the mouse doesn't want to work. So, so essentially, before I go to the line by line of this code, the premise behind this setup or this research study was that they had a simple convolutional network. They were trying to predict the classification of the images, right? And for their model, they used this Lunette with the sigmoid function and ReLU, because for some reason they said we only want to have it a second step differential, so that it doesn't use ReLU or anything like that. But yeah, 3 layers, and then with just a forward function as well. So, and the weights are uniformly distributed as well in this model. So the model, the database that they're using for this training is Cypher 100. So Cypher 100 essentially exists of thousands upon thousands of images of 32 by 32 bits or pixels. So relatively small, relatively good. And essentially in the setup, we get our data parameters of the class. So first we choose an index image, right? For any image we can choose, we want to run. And after that, we load the model itself. Once we load the model, we have to get the approximate kind of predictor and also the Y criterion and the gradient itself, because we'll use that afterwards for the algorithm to find out the approximate distances. And then also, yeah, of course, the original kind of gradient. After that, we create our dummy data. So it's dummy data and dummy labels, which are used hand in hand with the original gradient to, again, enhance basically the dummy data to look like the training data. And this is the optimizer that I mentioned, the LBFGS, that works with the limited memory. Edging noise, this was our own addition. So this wasn't this didn't exist before, because the research essentially just showed how the attack works, but they didn't show how they would add the noise specifically during the training process. So for our best estimate, we said, what would happen if we just add some random noise, whatever it is, in this case scenario, 1%, to the gradient that they produce anyway. And this is the meat of the whole kind of attack itself. So as they're going through, they first create a prediction on their dummy data, right? Then they create the one hot label from their dummy label to utilize that to actually get their own main gradient and criterion for the loss. And then following that, this is the part where they actually calculate the distance and feed it backward in the layers. And then they close that function in and essentially try to recreate or iterate over a few steps to improve their training kind of image or the source. The iterations here are kind of absolute, so it's like you don't have to put 200, you can put 100, 300, but essentially for the sake of running time, I decided maybe 200 is all right. And so yeah, so this is kind of the end of the whole setup, that essentially these kind of 20 lines of code here will do all the work, but if I run it, hopefully, it doesn't cache anything and it works. So yeah, so as you can see here, the first iteration, the distance difference is like around 54, but then as it tries to progress, the distance does reduce, reduce, and reduce further, and we can see that I am running here with the original gradient. So at the end of it all, it will show you the index image, I think, then the label image, and then also the layout of all the other images together. Yeah, and yeah, as you can see, it's already on zeros, but 200 is 200. So this is the main image. As you can see, it started with random noise as our dummy data, and then as it iterated and went through the optimizer, it did actually generate the proper image, and you can see that here at the end is where like you still had some pixels left over, but after that it's essentially a very good copy. And so yeah, you can see that this was the original input, which is not too clear, and this is the random noise that was there. Now, if I close all of this and I change the original gradient used to our own gradient, save it, run it, then hopefully the idea being is that it will produce some representation of that image, but there will be some noise laid over it, which will be very visually pleasing to see that, like, yeah, the noise does get added. But in theory, you can then play around with your accuracies and to see how you can actually work it out to be useful for your own needs. Yeah. So yeah, you can see, like, boom, there's a load of noise added. You already can't really define what the hell was underneath the image, but you can see that the original image was this, right? And so some of the drawbacks of this work is that although it's very good, there's a lot of developments since 2019 in the most recent things. So one of them being optimizing the algorithm that you're using. So here they use the LBFGS optimizer, but it was very memory limited. So they couldn't try to work on bigger data sets, for example. Another thing was, as they mentioned earlier, that it only works on smooth neural models. And also, they had some other people who were doing the distance calculation differently. So they were doing it on cosine similarities or something between the gradients rather than actual direct Euclidean kind of distances. And bigger data sets, yeah. So there are some awesome papers which like show almost a high pixel image of a Dutch hound or like German shepherd, and you can get pixel to pixel the actual dog's photo. So it's crazy, yeah. And also in terms of defense mechanisms, they offer some good solutions, yeah. That's kind of my presentation overall. If anyone has questions, please do ask.
So you added noise to the gradient. How well does the model still perform?
That was a good question. I've never tested it on this one. Okay. Yeah, thank you.
So I've got a question about the leakage attack.
Yeah.
What you've just shown there of recovering some training data in the original model. So if there was a classification model, let's say it was just saying this is a face, right, and the training data is my face and Max's face.
Yeah.
It couldn't return both separately, no? It would return what, like an average of those two?
So they did some studies on batch processing. So they did not have a very successful rate. So in terms of the faces, it would be similar to what the GAN model produced. So it's like you'll have the approximate faces of either one of you. But it wouldn't work, crazily well enough. But there are some other researchers that did kind of recreate batch processing and batch prediction, or like gather of training information, So again, there is a lot more kind of detailed work on, it's like bigger algorithms, bigger processing power, but essentially it's sort of doable, But again, no, the accuracy wouldn't be too high enough, then yeah, so some of the personal speculations from this reading material was that essentially rather than adding the noise to the gradient itself, we're wondering whether encryption works better, because essentially you can save the gradient, you don't have to actually destroy it, and you can add some key pair sharing to it. So that actually works quite well, but it can be kind of time consuming, as they said, or like with the setups. Google has recently also worked on mixing differential privacy with security aggregators. So it's essentially a topic of like encrypting the gradients, but also sharing them to the main aggregate server, or masking some of the gradients, but in such a way that once they're all together, they represent the main gradient that's used for the training model. So it's a really interesting topic in terms of like development, data privacy, and how you can make it efficient, because stochastic gradient was the first step, but paid is quite interesting, and I'll add the links to the YouTube description. Yep, thank you.
Brilliant. We'll close out there. Thank you very much, Andrii.
Thank you.
I particularly enjoyed the how intuitive that visual adding noise and then we do the attack again, and there is the difference was as a way of sharing it. And I've learned an awful lot about differential privacy today. I think it's sort of fascinating and a nice change of pace for this series. Speaking of which, we will be back in just under a month, I believe, with our next session, which will be on spatial data science. We will have, is it Pippa in? Is it Pippa in who'll be talking? Yeah, so Pippa will be joining us to talk about spatial data science. I think it's going to be a really fun session. It'll be the 4th of October, there or thereabouts. Until then, thanks everyone for joining. Thanks everyone who asked questions, and big thank you to Andrii
Cheers.
for
thank you very much.
Cheers all. Bye.
Bye-bye.